So we just got finished using the standard candles, supernovas, in order to figure out how far away objects are. But there's one last technique that is useful for measuring distances that are even greater than this number. And so that's going to be Hubble's law. And so this is going to be useful for measuring the distance from Earth to superclusters of galaxies. So if you remember, this was good out to clusters of galaxies, but now we want to go out to superclusters of galaxies, and we're going to use Hubble's law. So in order to understand this one, you need to know that space and time are expanding. According to general relativity, space and time go together to make space-time. And we think that the entire universe is expanding in both space and time. And so there is something that is similar to the Doppler effect, but it is a general relativity type concept. And so we're going to call this the cosmological red shift. And it's very similar to the Doppler effect, so that if something is moving away from us, it's going to be red shifted when that happens. So what we're going to do is we're going to look at a spectrum. And so if the spectrum is inside the laboratory room with you, it's not moving towards you, it's not moving away from you, then that means that it's going to have a particular spectrum when you look at it through your diffraction grating. Okay, but if we take this source of light and it's moving away from us, then it's red shifted, and so then that would mean that this line here would shift over to here somewhere, and then this line would shift over to here, and then this line would shift over to here. So the lines will shift towards the red end of the spectrum, which is over there. Now if the source of the light is moving even faster away from us, then it's going to be red shifted even more. Okay, so this line here is this line, but you notice it's been shifted even more towards the red end of the spectrum because it's moving away from us even faster. And so that's what that chart underneath us is saying. So this is a real effect because of the expansion of space and time. It's going to change our perception of the colors being produced by light. So, introduce Edwin Hubble. So Edwin Hubble was born in 1883, died in 1953. And so he's a very famous astronomer, and he plotted the velocity of nearby galaxies versus their distance. And notice that he got a line. Okay? Then he calculated the slope of that line, and it turns out that it's a constant. Anytime you see a straight line on a graph, that means something is constant. He calculated that constant, and it turned out to be 22 kilometers per second per mega light year. So capital M stands for million. 22 kilometers per second per million light years. That was the constant that he came up with, and it's called Hubble's constant. Okay, now how can we use this in order to figure out how far away an object is? So we're going to be looking at an object, looking at the light that it produces. We'll pass it through the diffraction grating and then look at its spectrum, and we're going to observe how much did it shift. So our first equation, there's two equations that we're going to use in order to figure out the distance to the object. The first equation is going to allow us to calculate the speed of the object. So that's going to be the letter v. So the speed v is going to be equal to, we're going to take the speed of light, c, 3 times 10 to the 8th meters per second squared, meters per second, and then we're going to multiply that by the change in the wavelength. So if we know this wavelength here, and if we know this wavelength here, we're going to subtract those two wavelengths. And that's the change in the wavelength. Okay, and then we're going to divide that by the original wavelength. So that's lambda sub 0. Can you see that? All right, there you go. So divide by lambda sub 0. So that's the original wavelength when it's at rest in the laboratory. This is the change in the wavelength up here. Then we multiply it by the speed of light, and that gives us the speed that this galaxy is moving away from us because of the expansion of space and time. Now we're halfway there, because all we've got to do is then to figure out the distance r to that thing. We're going to take our speed, whatever it is, from this equation up here, and all you got to do is divide by 22, because that's Hubble's constant. So take the speed from this equation, divide it by 22, and then that's going to be the distance to that galaxy in mega light years. All right, so here's an example of how you would use the formula so that you have a spectrum that has a rest wavelength of 402 nanometers. That's the unit of distance. The same line in a distant galaxy has a wavelength of 405 nanometers. How far away is it? So you're given the new wavelength is 405. The old wavelength was 402. So first you're going to find your speed. Now this one is kind of unusual. In the speed of light, instead of using 3 times 10 to the 8th meters per second, we're going to use 3 times 10 to the 6th kilometers per second. Okay, so notice, sorry about that, 3 times 10 to the 5th. So in order to have the units of kilometers per second in Hubble's constant, then that means we need to use for the speed of light 3 times 10 to the 5th, which is 300,000. So we're going to take 300,000, multiply it by the change in the wavelength, which is 405 minus 402. Okay, then divide that number by 402, and that gives us our speed. Then take that number, divide by 22, and that turns out to be 102, and then stick the unit on there, mega light years. So that's how we can now figure out the distance to that object. So if we put this all together, I'm going to come back to this. You have this chart right here. So this chart is the summary of everything that we've talked about. So we said that for small distances, use radar imaging. That's over there on this side of the chart. Then, if you want to figure out something that's further away, use geometric parallax. Then something further away, use spectroscopic parallax. Then something that's further away, Cepheid variables, Tully-Fisher, standard candle, and then Hubble's law. So it's just amazing that we can measure all of these different distances. So we're going to take a break, and when we come back, we are going to talk about why is Hubble's law, or why is Hubble's constant, why is it so important that we know what the value of Hubble's constant is? And we'll talk about that in our next segment.